Hi, in this video we will be taking a look at the EdExcel A-Level Maths Paper 3, which covers the statistics section from the October 2020 series. Question number 1. The Venn diagram shows the probabilities associated with 4 events A, B, C and D, and for part A we have to write down any pair of mutually exclusive events from A, B, C and D. Now, when we see the word mutually exclusive, we should be thinking to ourselves, these are events which cannot happen at the same time. And if we take a look at our Venn diagram, the events that cannot happen at the same time, well, we have A and C, those don't overlap, so they can't happen at the same time. We have D and B, those don't overlap, so therefore D and B are mutually exclusive, and D and C don't overlap, so therefore D and C are mutually exclusive. So we see A and C, D and B, and D and C are all mutually exclusive events. Part B of the question, given that the probability of B is equal to 0.4, we have to find the value of P. So what this means over here, all these different values must add up to 0.4. So, for part B, knowing that the probability of B is equal to 0.4, we have the 0.24 plus the 0.07 plus P. This is equal to 0.4. Okay, and therefore 0.24 plus 0.07, that's 0.31, so we have 0.31 plus P equals 0.4, and therefore the value of P is equal to 0.09. For part C of the question, given also that A and B are independent, we have to find the value of Q. Now, if we know events are independent, if we go to the formula book, we have different formula for independent events A and B. And crucially, you can see here that for independent events, the probability of A and B is equal to the probability of A times the probability of B. Now, the reason I want to use this formula here is because if I know the probability of A, I can use that to find out what Q is. And also, because we have the probability of A and B, that refers to this intersection, we know the probability of B, and from that we can find the probability of A. So if A and B are independent, then probability of A and B is equal to the probability of A times the probability of B. Now, so far, we know that the probability of B, that's given to us as 0.4. We can see over here the probability of A and B from the diagram, that's 0.24. So from this we can find out the probability of A. So we have over here 0.24. So this over here is the probability of A and B. This is equal to the probability of A multiplied by the 0.4, which is the probability of B. And from this we can find out the probability of A. The probability of A is therefore equal to 0.24 divided by 0.4, which is 0.6. Now, knowing that the probability of A is equal to 0.6, these values here of Q, the 0.16 and the 0.24, must all add up to give the 0.6. So, knowing the probability of A is equal to 0.6, we have over here Q plus 0.16 plus 0.24. All this is equal to 0.6. So simplifying all this, we have Q plus 0.4. This is equal to 0.6, and therefore Q is equal to 0.2. Now for part D of the question, given further that the probability of B dash given C is equal to 0.64, we have to find the value of R and then find the value of S. Now what this means is over here, we're looking at something is not B given we have C. Now the probability of C, that's equal to R plus P, and the probability that something isn't B given C, that's just R. So we have over here, for part D of the question, the probability of something not B given C is equal to 0.64. So using this, well, we have C, so that will be R plus P, and not B given C, we have the R on top, and all this is equal to 0.64. So multiplying through by R plus P, we have R equals 0.64 R plus 0.64 P, and tidying all this up, we have 0.36 R equals 0.64 P, and we know what the value of P is. We worked that out previously to be 0.09. So we have 0.36 R equals 0.64 multiplied by 0.09. So from this we can work out the value of R. So with our calculator, we have 0.64 multiplied by 0.09, and then we divide this by 0.36, so we get a value of 0.16. So we have R equals 0.16. And now to work out the value of S, we should recognize that the sum of probabilities is equal to 1. So each of these values added together must equal 1. So if we add those values together, we get 0.2 plus 0.16 plus 0.24 plus 0.07 plus 0.09 plus 0.16 plus S. This is equal to 1. And if we add up all these numbers, we get 0.92 plus S equals 1, and therefore S is equal to 0.08. Question number 2. A random sample of 15 days is taken from the large dataset for Perth in June and July 1987. The scatter diagram in figure 1 displays the values of two of the variables for these 15 days. So we see over here we have some variable along the x-axis and another variable along the y-axis, and we don't know what those are yet. But for part A of the question, we have to describe the correlation. we see over here for part A, we have a negative correlation. Now for part B of the question, the variable on the x-axis is daily mean temperature measured in degrees C, and using our knowledge of the large dataset, we have to suggest which variable is on the y-axis and state the units that are used in the large dataset for this variable. Now, we said over here we have a negative correlation, and along the x-axis we have daily mean temperature. Now, you should be familiar with the variables from the large dataset. So if we go to the large dataset, we're looking at Perth 1987. So that's in this tab over here, and we've got the various pieces of data shown here for May to October, and we're looking at June to July. But crucially, we should be thinking about the variables that are given. Obviously, we're not going to use the daily mean wind speed because that will be incorrect, as this is a qualitative piece of statistic. We've already been given that we have the daily mean air temperature, and one thing that will give a negative correlation with the daily mean air temperature will be the rainfall. And that makes sense. If you look at these months over here, hopefully you can see from the various pieces of statistic, as one variable increases, in other words, as the daily mean temperature increases, the rainfall would decrease. So we have rainfall as our variable on the y-axis. It has units, millimeters. Part C of the question, Stav believes there is a correlation between daily total sunshine and daily maximum relative humidity at Heathrow. He calculates the product moment correlation coefficient between these two variables for a random sample of 30 days, and he obtains a value of R being minus 0.377. And we have to calculate a hypothesis test at the 5% level of significance to investigate Stav's belief. We should state clearly our hypotheses and our critical value. Now, what you can hopefully see from the information given in the question is that we have a two-tailed test. The reason for that is we don't know if there is a positive or a negative correlation. The only thing we're checking is if there is any correlation at all. So we should use a two-tailed test. So, for part C of the question, our null hypothesis we have over here, rho is equal to 0, and our alternative hypothesis, we have rho doesn't equal 0. And when we come to find out our critical values, so for our critical values, we're testing at the 5% level of significance. So on either side of the tail, we will be looking for alpha over 2. So here we have 5% over 2, which is 2.5%. And the critical value for 2.5%, if we go to our formula book, you would see over here the critical values for the correlation coefficients are shown here. Now, we have a sample size of 30 and we're looking at 2.5%. So 2.5%, we're looking down this column here. So therefore, the value we're after is this 0.3610. So our critical value, RC, that's equal to plus minus 0.3610. And at this point, I think it will be a good idea to sketch a quick diagram to help visualize where we would reject H0 and where we would accept H0. So for our critical values, we've got over here this 0, okay? So we have over here a 0, and we've got the -1 effectively here and a 1 effectively over here. And here we've got the -0.3610, and here we've got 0.3610. And where we would reject H0 would be over here. So in these regions we would reject H0. So let's just add that here. We would reject H0. And the value that Stav found was -0.377. So the -0.377, that's over here somewhere. So here we have -0.377. We're in the region where we would reject H0. So therefore, we reject H0. And therefore, there is evidence to suggest at the 5% level of significance that there is a correlation between daily total sunshine and daily maximum relative humidity. For part D of the question, on a random day at Heathrow, the daily maximum relative humidity was 97%, and we have to comment on the number of hours of sunshine you would expect on that day, giving a reason for your answer. So, humidity is high and there is evidence of correlation from part C, and we know that R is negative. So if we were to quickly sketch this situation out, we would have something looking like this. We have humidity here, S over here, we have R which is less than 0, so we have some sort of a negative correlation. Okay? Now, if the humidity is quite high, we would expect the amount of sunshine to be quite low. So we would expect the amount of sunshine to be lower than the average for Heathrow. Question number 3. Each member of a group of 27 people was timed when completing a puzzle. The time taken, X minutes, for each member of the group was recorded. These times are summarised in the following box and Wixer plot. So we have to find the range of times. Now the range is defined as the largest value minus the smallest value. And you have to be a bit careful here. We don't take this value to be our maximum, rather we take this value to be our maximum, even though it's an outlier. And of course the minimum is over here. Okay? So we have the range which is the maximum minus the minimum. We have a maximum here at 68, a minimum here of 7. So therefore the range is equal to 68 minus 7, which is 61. For the next part of the question, we have to find the interquartile range of these times. The interquartile range is defined as the upper quartile minus the lower quartile. So we see here we have a upper quartile of 25, a lower quartile of 14, so the difference between 25 and 14, that's equal to 11. So we have the interquartile range being 11, and don't forget, add your units. So here we have 61 minutes for the range, and the interquartile range, that's 11 minutes. For part C of the question, for these 27 people, the sum of the x's is equal to 607.5, and the sum of the x squareds, that's equal to 17,623.25, and we have to calculate the mean time taken to complete the puzzle. So the mean over here, we'll call the mean x bar, that's equal to the sum of the x's divided by n. So we have the sum of the x's, 607.5, we have the sum of the n's, 27. So dividing these, if we use our calculator, 607.5 divided by 27, it turns out we get 22.5. For part D of the question, we have to calculate the standard deviation of the times taken to complete the puzzle. Now if we go to the formula book, the formula for the standard deviation, that's shown over here. And you can see that the standard deviation is equal to the square root of the sum of the x squareds divided by n minus the mean squared. And we know all these values. So for part D of the question, the standard deviation, we'll call this standard deviation sigma, that's equal to the sum of the x squareds divided by n minus x bar squared. So this over here is our formula for the standard deviation, and substituting our known values, we have 17,623.25 divided by 27 minus 22.5 squared, and then all of this is square rooted. So if we work all of this out, we have the square root of 17,623.25 divided by 27 minus 22.5 squared, so we get 12.1 to, we'll say 1 decimal place. So we get 12.1 minutes to 1 decimal place. Now, for part E of the question, Taruni defines an outlier as a value more than 3 standard deviations above the mean. And for part E, we have to state how many outliers Taruni would say there are in these data, giving a reason for your answer. So, first of all, we have an outlier if the values lie above the mean plus 3 standard deviations. So, working this out, we have 22.5 plus 3 lots of the 12.1. So, working this out, multiplying this by 3, and then adding 22.5, it turns out we get 58.8. So we have here 58.8 minutes. Okay, so anything above this will be an outlier. So if we go back to the question, the 58 point something, that's over here somewhere. So anything beyond this point is where we'll have an outlier. And we see over here, we only have one outlier. So therefore, in conclusion, we have only one outlier, which is the 68 minutes. For part part F of the question, Adam and Beth also completed the puzzle in A minutes and B minutes respectively, where A is greater than B. And when their times are included with the data of the other 27 people, the median time increases and the mean time does not change. We have to suggest a possible value for A and a possible value for B, explaining how your values satisfy the above conditions. Well, we'll take this one step at a time. If we go back to the box and whisker plot, you can see here, so far, the median is 20. And we were told in the question that the median time increases. And if the median time increases, both the A and the B must be greater than 20. So the median for the 27 people is 20, and if we now include these extra two values, the median time increases, and if the median time increases, A is greater than 20 and B is greater than 20. We also know from the question that the mean time does not change, and we calculated here the mean was 22.5. Okay? So the mean for the 27 people, that's 22.5, and since the mean does not change, the mean for the 29 people is 22.5. Now, with this, we can find out what A and B must add up to. Now, the reason I say that is, we know that the sum of the x's for the 27 people is 6 or 7.5, and if we include these values of A and B, this time for 29 people, the mean now becomes 607.5. This was for the sum of the x's of 27 people, and then we have A and B. So here we've got 29 pieces of data added together, and of course we divide all this by 29, and we know all this is equal to 22.5. So with this we can find out the values of A plus B. So A plus B, if we work this out, we have over here 29 times by 22.5, and then we subtract off the 607.5, it turns out we get 45. So A plus B must equal 45. And we also know A is greater than B. So we need two numbers of A and B, which add up to give 45. A must be greater than B, and both A and B must be greater than 20. And we can choose various different pairs, but essentially one possible pair, we could have A equals 24, say, and B equals 21. This satisfies these conditions. Now, for part G of the question, without carrying out any further calculations, we have to explain why the standard deviation of all 29 items will be lower than our answer found in part D. And in part D, of course, we found the standard deviation to be 12.1 minutes. So both values over here will be less than one standard deviation away from the mean, and we see that over here, and therefore the standard deviation for all 29 values will be smaller. Question number 4. The discrete random variable D has the following probability distribution as shown here, where k is a constant, and we have to show that the value of k is 600 over 137. Well, what we should know so far is that probability adds up to 1. So the sum of probabilities is equal to 1, and using this, if we add up all those probabilities and set that equal to 1, we have over here k over 10 plus k over 20 plus k over 30 plus k over 40 plus k over 50, all this added together is equal to 1. And if I factorise out a k, we have k lots of 1/10 plus 1/20 plus 1/30 plus 1/40 plus 1/50. And all this is equal to 1. So we have 1 over 10 plus 1 over 20 plus 1 over 30 plus 1 over 40 plus 1 over 50. Turns out we get 137 over 600. So we have 137k over 600 equaling 1, and therefore k, you can clearly see that's equal to 600 over 137. That's what we wanted to show. Now for part B of the question, the random variables d1 and d2 are independent and each have the same distribution as d. We have to find the probability of d1 plus d2 equaling 80, giving our answer to 3 significant figures. Well, if we think about d1 and d2 equaling 80, we need 2 values of d which add up to give 80. So, for part B of the question, the probability that d1 plus d2 equals 80, let's think about the different combinations we can have. We can have d1 equals 30 and d2 equaling 50. That gives a total of 80. Okay? Or we can have the probability of d1 equaling 50 and d2 equaling 30. 50 plus 30 gives the 80. Or we can have d1, which is equal to 40, and d2, which is also equal to 40. 40 plus 40 gives the 80. Now, the probability that d1 equals 30, d2 equals 50, we have k over 30 and k over 50. So what we have over here then is k over 30 multiplied by k over 50, and then we have d1 equaling 50 and d2 equaling 30. Well, here we have k over 50 and k over 30. So here we have k over 50 multiplied by k over 30, and now for d equaling 40, that's k over 40. So we add on k over 40 times by k over 40. So if we get an expression in terms of k, well, if I factorise out a k squared, we have over here k squared lots of 1 over 1500 plus 1 over 1500 plus 1 over 1600. And of course the way I got that was I noticed k times by k gives the k squared, and then 30 times by 50 and the 50 times by 30 gives the 1500, and 40 times by 40 gives this value over here. So if I tidy all this up, we have 1500, we have 1 over 1500 times by 2 plus 1 over 1600. So here we get 47 over 24,000. So here we have 47k squared over 24,000, and knowing the value of k, we have 47 over 24,000 multiplied by 600 over 137 squared. So if we work this probability out, we have over here this value times by 600 over 137 squared, we get 0.0376. So we get 0.0376 to 3 significant figures. For part C of the question, a single observation of D is made. The value obtained, D, is the common difference of an arithmetic sequence. The first 4 terms of this arithmetic sequence are the angles, measured in degrees, of quadrilateral Q. We have to find the exact probability that the smallest angle of Q is more than 50 degrees. Well, if we have 4 terms of an arithmetic sequence, and we have common difference D, you can see here that the angles are, well, the first angle, that will be A, the second angle will be A plus D, the third angle will be A plus 2D, and the fourth angle will be A plus 3D. You see over here we have a common difference of D. And we were told that the sum of the first 4 angles, that will be the sum of the angles of a quadrilateral, so we have these 4 angles added together equaling 360. So in other words, we have S4, which is equal to 360, so we have A plus D plus A plus 2D plus A plus 3D, and if we add all these together, we get 360. So we have 4A plus 60, which is equal to 360. So if we simplify all this, you can see 2A plus 3D is equal to 180. And we were told that the smallest angle must be greater than 50, and we're finding out that probability of A being greater than 50. So we know that the smallest angle, well, that's going to obviously be A. And we also know that the smallest angle must be greater than 50. Now, over here, because we're calculating the probability of A being greater than 50, what would pop into my head is, at some point I need to use this table over here. And I can use this equation here, the 2A plus 3D equals 180, to find out which values of D are acceptable, given this condition over here. So let's just write that down. So we want the angle A to be as small as possible, but greater than 50. And if we use the probability distribution in conjunction with what we have over here, first of all, if D is equal to 10, now, just to emphasize, the reason I want to use the probability distribution in this question is because that will allow me to find out the probability. So there must be certain values of D which satisfy this condition. And let's find out which values of D satisfy these conditions. So if D is equal to 10, we have 2A plus 3 lots of 10 equals 180. So we have 2a equals 150. And therefore a is equal to 75. Well, here we see a is greater than 50, so that's a possible value we can use. We can use the value that d is equal to 10. Let's just give this a tick. Let's see what happens if d equals 20. We have 2a plus 3 lots of 20 equals 180. So we have 2a equals 120. So therefore a is equal to 60. This is greater than the 50 degrees, and we've got a value of d which is perfectly legit to use. Now let's see what would happen if d is equal to 30. If d is equal to 30, we have 2a plus 3 lots of 30, which is equal to 180. So we have 2a, which is equal to 90, and therefore a is equal to 45. We don't want to use this value of d when we come to work out the probability, because we see over here a is not less than, a is not greater than 50 here. A is indeed less than 50. And we can try out a similar thing with over here d equaling 40. So if d equals 40, we have 2a plus 3 lots of 40, which is equal to 180. 2a, that's equal to 60, and therefore a, that's equal to 30. Again, we're not going to use this. We want a to be greater than 50. And finally, if we try that d equals 50, we have 2a plus 3 lots of 50, which is equal to 180. 2a, that's going to equal 30. So therefore a is equal to 15. Again, we don't want to use this. We want d to be greater. We want a, to be greater than 50. So the only values of d we can use are d equals 10 and d equals 20. So what does that mean? Well, first of all, let's just write that down. So the only possible values are d equals 10, which implies a equals 75, or we can have d equals 20, which implies a is equal to 60. And both of these will be the smallest values of a, both greater than 50. So therefore, the probability that a is greater than 50, that occurs when d is either equal to 10 or d is equal to 20. So this is equal to the probability that d equals 10, or the probability that d is equal to 20. So probability that d equals 10, that's going to be k over 10, and that's from the table. So here we have k over 10 plus k over 20, that's the probability that d equals 20. So here we have over here k lots of 1 over 10 plus 1 over 20. So we have 3k over 20, and knowing the value of k, we have 3 over 20 lots of 600 over 137. Now over here we have to leave our answer in exact form, and if we do the arithmetic, it turns out the probability that a is greater than 50 is 90 over 137. Question number 5. A health centre claims that the time a doctor spends with a patient can be modelled by a normal distribution with mean of 10 minutes and a standard deviation of 4 minutes. Using this model, we have to find the probability that the time spent with a randomly selected patient is more than 15 minutes. So for part A of the question, we have x, which is normally distributed with parameters 10, and 4 squared. And we're looking at the probability that x is greater than 15. And if we use our calculator, we can go to the normal cumulative distribution. Now, I think it will help to sketch a diagram for this question. We have something looking like this, and we've got a mean of 10, and we've got this 15 over here somewhere, and we're finding out this probability essentially. Okay, so you can see over here where it says our lower, let's choose 15. Upper, we'll choose something big, something like 1,000,000. Sigma here, that's going to be 4. Mean, that's going to equal 10. So it turns out to 3 significant figures, we get 0.106. So that's the probability. Okay. So part B of the question, some patients complain that the mean time the doctor spends with a patient is more than 10 minutes. The receptionist takes a random sample of 20 patients and finds that the mean time the doctor spends with a patient is 11.5 minutes. State your hypotheses clearly and use a 5% level of significance to test whether or not there is evidence to support the patient's complaint. Well, over here, we will be taking a look at a sample mean normal distribution. So, first of all, let's write down our parameters. We have a sample of 20 patients selected, so x bar. This is normally distributed with parameters 10. That's our mean. And we have our variance shown here. 4 over the square root of 20 squared. Okay, so we're carrying out a hypothesis test, so our null hypothesis, that's telling us that mu is equal to 10, and our alternate hypothesis, we have the mean being more than 10 minutes, and that's what the patients were saying. The doctor spends more than 10 minutes with a patient. And if we go to the question, the receptionist finds the mean time the doctor spends with a patient is 11.5 minutes. So if we find out the probability that x bar is greater than the 11.5, we can then compare this with the 5% to test to see whether we accept or reject H0. So again, it's quite useful to draw a diagram to illustrate the problem. So here we've got 10 and 11.5, that's over here somewhere, and in this region we would reject H0, this region we will accept H0. So working out this probability, so here we've got the 11.5, our lower limit is the 11.5, upper limit something really big, something like 10 to the 6. Sigma over here, that's going to equal 4 divided by the square root of 20, and the mean, that's going to equal 10. So it turns out we get over here 0.0467, etc. And what you see over here, this is less than the 5%, and therefore we can reject H0. So if we put our answer into context, we can see here that there is evidence to support the complaint. Now for the first part of Part C, the health centre also claims that the time a dentist spends with a patient during a routine appointment, t minutes, can be modelled by the normal distribution where t is normally distributed with parameters 5 and 3.5 squared. And we have to find the probability that a routine appointment with a dentist takes less than 2 minutes. Okay, so what we are doing in this question, for part CI, we know that t is normally distributed with parameters 5 and 3.5 squared. We're looking at over here the probability that t is less than 2. So let's just double check I've wrote that right. Yeah, it takes less than 2 minutes. So we can work this out again. It might be quite helpful to draw a diagram to help illustrate what's going on. We have 5 over here, and we've got this 2 over here. And we're finding out this probability here. So our lower limit, something really small, something like this. Upper limit, that's 2. Sigma here, that's 3.5. Mu, that's equal to 5. So it turns out we get a probability of 0.196 to 3 significant figures. Okay, and now for the next part of the question, we have to find the probability that t is less than 2 given t is greater than 0. Again, I think it will be a good idea to sketch this problem. So we are looking in this question, the probability that t is, if I just go back, that t is less than 2 given that t is greater than 0. So if we sketch this out again, we have over here a normal distribution, something like, draw it neatly, something like this. We have mean 5. Where t is greater than 0, let's suppose over here 0 is here somewhere. Okay, t being greater than 0, that's shown in blue over here. So this over here is where t is greater than 0. And we're looking at the probability of t being less than 2 given t is greater than 0. So the probability that t is less than 2 given that t is greater than 0, essentially, if I underline the entire bit, we've got this 2 over here somewhere, and we're looking at the probability that t is less than 2 given this bit over here. So what we're looking for is essentially this area over here. Okay, so that's the probability we're looking for. So we have to be a bit careful here. We're not going to be using this value because t being less than 2, that implies from here, so let's just move this to this side. What you see over here, t being less than 2, this is implying that we're looking at the probability that t is in between 0 and 2. And it makes sense, we can't have any negative values taken into account because time obviously must be greater than 0. And here we've got over here probability that t is greater than 0. Okay, so let's just write this in the center. So if we work this out, for the line over here we've got a lower limit of 0 and upper limit of 2. Values remain the same as shown, so here we get 119, etc. the bit at the bottom. So let's just store this into A actually. And then the bit at the bottom where t is greater than 0, lower limit is 0, upper limit is something really big, something like 1,000,000. So here we get 0.923, etc. So we get here A divided by this, which is 0.129, again to 3 significant figures. Okay, and now we have to explain why this normal distribution may not be a good model for t. So the current model suggests a non-negligible probability of t values less than 0, which is impossible as time is greater than 0. And now for part D of the question, the dentist believes that she cannot complete a routine appointment in less than 2 minutes. She suggests that the health centre should use a refined model only including values of t greater than 2. And we have to find the median time for a routine appointment using this new model, giving an answer correct to 1 decimal place. Well, the trick in this question is to realise we have to find the median time. So from a normal distribution, median is equal to mode, which is equal to mean. Okay? And if you essentially compare this with a z value, so for part D, if we take a look at a z table, currently we've got something looking like this. We've got a mean of 5 and the equivalent z value is 0. Okay, and the median of a probability distribution will be 0.5. Now that makes sense even if you go to the tables. So let's just go to the correct page. In the statistics section, what I've said there makes complete sense. As soon as I find the page, that is, where we've got the z value, we've got a corresponding p-value of 0.5. Okay, so what does this mean? Essentially, the median of a probability distribution is 0.5. Okay, so with that information, what are we looking for over here? Well, we're finding a new median time, okay? And she suggests that the health centre should use a refined model only including values of t greater than 2. So we're looking at values greater than 2, okay? And what we'll also note from the question is that the dentist believes that she cannot complete a routine appointment in less than 2 minutes. In other words, the time taken is longer. So let's just illustrate what we need to do. We have over here the probability that t being greater than some value of t, given that t is greater than 2. Okay, so t being greater than 2, that corresponds to this bit over here. Okay, and this bit is what I said. She's saying it takes longer than 2. Okay, and all this is equal to 0.5, and this 0.5 comes from the idea of having a median time. Okay, so with this, obviously we can see here we have the p of t being greater than t over p of t being greater than 2. This is equal to 0.5. Okay, so how does this help us? Well, we can actually find out the probability that t is greater than 2, and we'll do this in grey actually. So the probability that t being greater than 2, we can work this out. We'll draw a quick normal curve. We've got our 5 over here, and we've got a 2 over here somewhere, and we're looking at essentially this probability over here. So if we go to our calculator, go to the normal cumulative distribution, we have a lower limit of 2, upper limit, sorry, something really big, sigma that's equal to 3.5, mu that's equal to 5. So it turns out over here, this value is equal to 0.804, etc. We'll save that answer for a second. So what we can see here then, we have the probability of t being greater than t, and our goal is to find this t over here, over this value over here of the 0.804, etc. This is equal to 0.5. So the probability of t being greater than t, we can actually find out what this is by multiplying this value by 0.5. So here we get 0.402, etc. So what we can now do is, again, if we sketch out a diagram to help visualize what's going on, we've got a normal over here, something like this. We've got our mean of 5, and here we've got some value of t, okay, and we're looking at where t is greater than t, and all this is equal to the 0.402. So this over here is equal to 0.402, etc. Okay, so with that, first of all, with this we can use the inverse normal. And for us to use the inverse normal, what we'd have to do is find out over here the probability that for us to use the inverse normal, we'd have to find this over here, the probability that t is less than t. And this is equal to well, essentially what I'm saying over here, actually, if I rephrase what I've said, I'm saying over here, the probability, no, I've done it correctly. So this bit over here is going to equal 1 minus this. So here we've got 1 minus the 0.402, etc. So 1 minus this, that's equal to 0.597, etc. So that's essentially what this is over here. So what we can now do is essentially use the inverse normal to work out this value of t. So therefore we can conclude over here t is equal to, if I use the inverse normal, so if we go to our calculator, option 3 for the inverse normal, the area is this, and mu over here, that's going to equal 5. Sorry, that's equal to 0 if we convert it into an equivalent z value. No, I think I've done that wrong. So this is equal to 5. And this is equal to 3.5. So I get a value of 5.86. We'll call it 5.9 minutes to 1 decimal place. Okay, So this over here is our final answer. Okay.